Welcome to Database Management Systems. I think this is going to be a very valuable course for those of you in the MBA program. It's a survey course, but it's a comprehensive introduction into a very important fields. It's in this class, we're going to present the basic concepts of SQL or relational databases, and also have a brief introduction to NoSQL databases, which are currently becoming very popular. So we are going to present the basic concepts of relational databases, and we'll go into data modeling. And a data model will be introduced that represents the entities and principles of a particular problem space. And it can be used for any type of logical data design. We're also going to be implementing the logical design into a traditional relational database. But we can also take that logical design and implement it into a NoSQL database as well. As for me, I'm a tenure-track professor at Shepherd University in the College of Business. I'm also an adjunct professor at UMBC in the Computer Science and Electrical Engineering division. And I work for Blue Glacier Group, which is a small firm in the intelligence community. I've been working with databases for 41 years and bring with me a history of how things were, why they changed, and the directions they are now going. I worked for Microsoft for 10 years as a senior architectural engineer for the SQL Server database and Visual Studio programming products. As for my academic background, I have bachelor's degrees, one in computer science and one in accounting, master's degrees, one in computer science and one in marketing, and a doctorate in management. Some 50 years ago, I was in your seat taking computer science courses at the University of Maryland back in 1971. The tuition was then $236 a semester, and you could take unlimited semester hours. And to put that in perspective, I worked at Beacons Moving and Storage, and I could earn that amount of money in 2 weeks. Prior to that, I was in the Marine Corps. So in addition to learning an interesting field in computer science, there's also the job consideration, and knowing NoSQL and data modeling will enhance your resume. Of course, naturally knowing relational databases will do that as well. Also, having done some projects in them, and we will be doing projects as a team in this class, that'll help your resume even more. Now, we have a lot of material to cover in one semester, so we organize the presentation of that material with PowerPoint. It's a good tool for organizing, presenting, and providing a study reference for massive amounts of information in a short period of time. We'll supplement PowerPoints with hands-on exercises. So you'll need to bring your PCs to class. I have tested the instructions, which are step-by-step, on both Windows and a Mac. We're going to cover modeling in the course, and modeling is important. This is how we organize our data in a database. We want to put it into subdivisions that we might call tables in a relational database. So We will do that with relational databases. But again, as I had mentioned earlier, once we have this model set up of how we want to organize our data into various entities, then we can not only physically implement that into a relational database, but also into a NoSQL database. So let's take a look at our Sakai website, and we'll go over what that's like. Here we see our Sakai website for the course. I'll get into student view so it might look a little more familiar to you. And it's working on it now. This may be one of the last semesters we use Sakai. I believe in the fall we're going to be using a different learning management system. So here's our course website on Sakai. Here's the course homepage. Gives you an introduction, a brief introduction to the course, brief description of it. We have our syllabus, and the syllabus is going to have a lot of useful information, including the grading, how grading will be determined, as well as how we can, with the schedule that we'll be following during the course. We also have our messaging. And this is a very effective way to communicate. I use this all the time. It's directly linked to Microsoft Outlook that you use in your normal Shepherd email. But it is very, you cannot send it to the wrong person, your homework assignments or whatever it would happen to be, because this is a closed session. Whereas oftentimes there's another G-Ray at Shepherd, and oftentimes students will send their homework to that other person. It's not a big deal. I just send them an email, hey, where's your homework? And we figure out what happened. But if you send your messages from Sakai messaging, you won't run into that problem. Most of our material is going to be in the resources folder on Sakai. And we have our lectures that we see here. And you'll have slides for each one of the lectures in the lectures folder. And you can review those prior to the class. We also will have, I'm going to be recording the sessions. I'm recording now, in fact, and I'll post the recordings for people who want to work online in the video lecture folder. We can see here's the video lectures, none posted yet, but there will be tomorrow. Go back to resources. And the other one I want to point out tonight is the hands-on exercises. We are going to be doing hands-on exercises in class. I'll be here to assist you with those. And The first one we'll do, and we'll do this later on this evening, is we're going to download our database system, and we're going to use SQLite. So I have hands-on SQLite. So we'll open that folder, and you'll see two subfolders in here. One for Mac, one for PC. The Mac will just have a database that you'll download. And it's a university database with a group of students, instructors, classes, departments, registration, and so on. And we'll be using this in examples throughout the course. You have, as Mac users, SQLite already pre-installed on your Mac. It comes with the Mac operating system. Let's go back to SQLite, the main folder. On the other hand, PC users do not have that luxury. So I have a zip file for them to download. One file in the zip is the same as what the Mac users get. It's a university database with students, instructors, classes, departments, and so on. The other is an executable for SQLite. So you'll create a folder for SQLite and just put that, unzip this into the folder, and you'll have SQLite ready to go. Okay, so that's our hands-on exercises. We'll have various types of hands-on exercises throughout the course. Some hands-on exercises where we have a business description and we then create a data model. Others where we will be given a problem and we'll use SQL to resolve that problem. Okay, any questions on the Sakai website? Okay, very good. We'll go back to our lecture here. So tonight we're going to start with chapter 1, which gives us an overview of database systems. So in this particular chapter, we're going to contrast data and information, look at what a database is, understand the importance of database design, and how databases have evolved from file systems in the past. In fact, when I started in programming, and again, this is 49, 50 years ago, file systems were the common way you stored data. You did not, it was very rare that you would have a database. It was mostly very high-end multinational companies that had enormous budgets that could afford that type of systems. Obviously, this has changed over the last 49 or 50 years. So we're going to look at some of the advantages databases have over that old way of doing things with file systems. And then look at the functions of a database management system. So first, information is data that's put into some conceptual framework to enhance our understanding. Just give an example of a database. Consider our university database example. Here we have entities of students, of instructors, and of courses. Now, in a relational database system, these entities are physically stored as tables. much like you find in Excel, where you have rows and columns. Then we also have application programs we will use to use that database. And we might do things like add new students, add instructors, add courses, register students for courses, generate class rosters, assign grades, and so on. In the early days, database applications were built directly on top of file systems. So over time, database management systems replaced the use of file systems, especially as the cost started going down. So a database management system contains information about a particular enterprise. It's a collection of interrelated data. It's also a set of programs to access the data. And it's an environment that is both convenient and efficient to use. Some of the database application areas are in banking, where you record transactions. In airlines, reservations are made, schedules are produced for the flights. Universities, registration of students, grading of students. In sales, we keep information about customers, products, purchases. Online retailers, we do order tracking or we customize recommendations. Manufacturing, we have systems on production, on inventory, on orders, supply chain, and even human resources. We keep track of our employee records, salaries, and tax deductions. Databases can be very large, and they touch almost all aspects of our life. So here we see an example of a database management system. We have end users, and they connect with the DBMS, and the DBMS then will access the database tables. We structure our database into tables with relational. We'll get into how NoSQL does this. But we have tables on customers, invoices, products, and so on. So one of the reasons we started using DBMS rather than file systems is because in the file system, we had multiple file formats, which meant that we had inconsistency in how programmers would access the data. We had duplication of information in different files. We had difficulty in accessing data. We had to write a computer program to carry out each task, whereas with the relational and the NoSQL databases, we have what's known as a console, which is a general purpose interface for us to use to query and get data out of our database. There's also integrity problems. You had difficulty in adding new business constraints or changing existing ones. There is also security problems. It's hard to provide user access to some, but not all of the data, because basically, if you granted access to the file system, people got access to the files. Whereas with database management systems, we can be much more granular in offering access. Likewise, file systems couldn't allow multiple users to access the database at the same time. Today, with database management systems, they do allow concurrent access by multiple users. So database management systems offered solutions to these drawbacks of the file systems that I've talked about. So here again, we see We have improved data sharing, security, access, decision-making, better data quality. Database management systems offer solutions to the problems we just went over. So, some history of the databases. In the 1950s and early 1960s, data processing used magnetic tapes for storage, and tapes provided only sequential access, and they had punched cards for input. In the late 60s and in the 70s, hard disks allowed direct access to the data. Network and hierarchical data models became widespread in use. Ted Codd, who was a doctor at the IBM Research, defined a relational data model. He eventually won the Turing Award for this work, which is the equivalent of a Nobel for computer science. And IBM Research then began its prototype System R. So we started getting some high performance for that era transaction processing for that time period. In the 1980s, relational prototypes evolved into commercial systems. And for the last 40 years, SQL has been the industrial standard. In the 1990s, we added data warehousing and data mining applications, and we saw the emergence of web commerce. In the early 2000s, we were able to store data in XML or XQuery formats. And now in the later 2000s, we're getting into giant database systems. So we'll have Google Big Table, things of that nature. The architecture of database systems is greatly influenced by the underlying computer system. And the underlying computer system on which the database is running can be centralized, client server, parallel, and distributed. A general purpose database has a wide variety of data and has multiple business domains using it. You can also have discipline-specific databases, and they contain data on specific subject areas. So, our normal database operation is going to be transactional. That means we're going to record transactions. We'll be writing information into the database. When we get a new transaction, we write it into the database. We also have and that's an operational database. Another type of database is an analytical database. And this is where we want to analyze the data that we have already stored in our database. Here we're doing reads. And so with that in mind, we can do some things that are not efficient for transactional, but greatly improve the efficiency of our analytical queries. So in this course, we're going to be studying transactional databases. A data warehousing course is where you learn how to model an analytic database. There's something that goes along with a data warehouse called online analytical processing, and that retrieves and processes data from a data warehouse. Business intelligence is another thing that comes along with data warehouses, and it captures the business data and generates information to support decision making. In the past, we were dealing with databases that had structured data. In other words, we knew the fields or columns. We knew what a name, we said, okay, 30, let's say that it has a 30 character string as a name, salary would be an integer, and so on. We knew exactly what everything was, and it was highly structured. Obviously, we have a lot more data than just this structured data, and it's very time consuming to add structure to this data. So now we also store unstructured data and semi-structured, and we will use things like text analytics to analyze that type of data. So we do have a data analytics course, and you will be taking that, and you'll see at least get a background that would enable you to then look into text analytics. Text analytics is a fairly advanced topic. So we'll be dealing with structured data in this course, the traditional data that we would usually work with. So we want to model our database. In other words, organize it with a good design. So we want to do a couple of things. We want to describe our data, describe relationships between our data, then have metadata, which is where we have descriptions about what our data is all about. And then we have data constraints. In other words, if salary is a field, we can say it's an integer, but a constraint might go farther. It might say it has to be an integer that's between 20,000 and 100,000, because that's a business constraint at the university. The relational model is the one that is widespread and is very effective for capturing transactions. The modeling technique we're going to use is entity relationship data modeling. And we'll be using that for database design. So here we see, again, conventional files versus the database. Files are a collection of similar records. Files are unrelated to each other, except in the code of the application program. A data storage is built around applications that use the files. Again, a database is a collection of interrelated files. Records in one file or table are physically related to records in another file or table. Applications are built around the integrated database. Now, a field is the smallest unit of meaningful data to be stored in a database. So it's an attribute about one of the entities we're interested in. So let's take student, for example. In the university database, we are going to be interested in an entity known as student. And we might be interested in the student's name, the department they're in, the number of credit hours they've taken, and their rail ID number. So those are 4 attributes in our logical design. And when we talk with users, they will tell us the type of things that they're interested in. And from that, we'll develop this logical design. Oh, they talked about students, they talked about instructors, they talked about departments. And for students, they were interested in the name, rail ID, department, and total credit hours. Those become our attributes in our logical model, and then we implement them as fields in our relational table. And the relational table, the field is a column. So we have for each record, which is a row, a student. And then each one of the columns represents a field for that student: the student's name, the student's department, the student's rail ID, and the student's total credit hours. So records is a collection of fields arranged in a predetermined format. In relational, we're going to have fixed length record structures. In other words, every record, it has the same number of fields, and each of the fields is going to have the same characteristics in terms of size and type. A file is a set of all occurrences of a given record structure, and a table is the database equivalent to a file. So we can have master files, we can have transaction files, document files, archival files, audit files, and so on. Both a sales department and a personnel department might keep those, as in the past, in electronic files. But if we keep in a database, we're going to have all of that done together for us. So the older file design methods had some problems that we see here. They asked the analyst to specify precisely how the records will be sequenced. That's the file organization, and then access, that's the file access. And a data architecture is a definition of how the files and databases are to be developed and how they're going to store data. A file or database technology that's going to be used, and the administrative structure for setting it up. So a database architecture is some combination of conventional files, operational databases that we have organized to get the information we are interested in. So some of the pros and cons of databases. One of the positives with a database is data independence from applications. So that means that it increases our adaptability and flexibility. Databases also have superior scalability to files and the ability to share data across applications. Some of the negatives of databases are it's a more complex technology than files, has somewhat slower performance, requires a fairly substantial investment in computer equipment and database experts. And if you get a professional database system like Oracle or SQL Server, a large price tag as well. But again, you get structural independence. You can change the file structure without affecting the application's ability to access the data. So the practical significance of data dependence is we have a logical format, and that is what we want to base things on, and a physical format. And that's how we take that logical basis and we actually physically implement it. And with the old file systems, we had dependence. Once we implemented it in this particular file system, we were dependent. if we made a change in the record structure of the file, all the programs would break and we'd have to rewrite each one of the programs. That's not the case with a database management system. We can change the structure of the table and the applications will still get the information they asked for. One of the things we want to avoid in our database modeling is redundancy, where we repeat the same information over and over again. Some of the implications of redundancy, if we don't minimize data redundancy, we could have security problems, we could have data inconsistency problems, and we can have anomalies. If we do updates and we've got duplicates of this information scattered all over the place, if we don't update them in all places, we could have some inconsistencies or data anomalies. And there's different types of data anomalies, and we'll go into these in class in the future, but we have update anomalies, insertion and deletion anomalies. So one of the problems is with databases, as I mentioned, is the need for database experts. And however, there's a lack of design and data modeling skills. So if you have those skills, obviously that's going to be a plus for your resume. And we're going to go over how you do database modeling. You know, today we're just getting a high-level overview of everything, but we will get into the nitty-gritty of how we actually design databases. So currently, our database management structure does a lot of things for us, as we see here. Eliminated most of the need for file systems and got rid of the problems associated with those. It stores our structures, relationships between those, gives us paths to access the data, and defines, stores, and manages all access paths and components. So here again, we see a contrast between the database and file system approach. Again, the file system approach is an old approach that was, for the most part, abandoned in the early 80s. From then on, the last 40 years, people have been using relational or tabular databases. And by tabular, I mean that the database table has a structure like an Excel spreadsheet where you can have rows of individual records and columns of the attributes we want to track for each individual record. Now, once we have a database set up, we have a whole infrastructure of support. Systems administrators, database designers, administrators, programmers, analysts, and of course, end users who use that database. A data dictionary is where we store information or descriptions about the data. For example, we would say a student's total hours is the total number of hours they have completed in their college career. And it is defined as an integer, and it has to be between 0 and 140, let's say. So it gives us a description of what's going on. Databases also allow us to improve performance. We can tune the database to get better performance. And likewise, we can put security in our databases to protect them. With a database, unlike with a file system, multiple users can access the same tables at the same time. We also have a very efficient way of backing up and recovering our data in the case of a catastrophic failure, like the tape the disk system crashes or the whole computer crashes. Now, we can access databases using an access query language. The query language for relational databases is SQL, Structured Query Language. And it's a very easy to learn system for selecting records and selecting records that meet certain criteria and telling the database what tables the information is stored in. We also have communications. The database can communicate across networks and across the internet for that matter. And we've gone over some of the disadvantages of database systems. More complex. There is a vendor dependence to some extent in increased costs. And here's a set of careers we see in the database field. Okay, any questions on our lecture? Okay, it'll take probably only a couple of minutes, but I want you to go to our Sakai website. And you remember where I showed you the folder for resources had hands-on exercises. Hands-on exercise 1 is what we'll be doing tonight. And for Mac users, you'll just create a folder where you're going to go during the semester to access our database. And you're going to download the database in the Mac folder of SQLite to that particular folder on your Mac. Again, SQLite comes pre-installed on the Mac. So to access it, all you have to do is open a terminal window on your Mac and then open the database. And it's .open space and then the name of the database UMBC. So try that. Windows users, there's an additional step. You will likewise create a folder, and you will download the zip file to that folder. You'll extract the zip file to that folder. You will then have SQLite in that folder. So you will have just by unzipping, you will have installed SQLite as well as the database. You'll do the same thing. You'll start up SQLite by opening a DOS command prompt, type in SQLite, space, and then the name of your database, UMBC, and you'll be in business. Okay, so let's get working on that. If you have any questions, raise your hand and I'll come by and provide assistance. Thank you.